New on Curiosity Stream. How do you connect a 16th century potato to limitless energy production? Could Napoleon's toothpick have a direct link to a machine that predicts the future? And how can a 1700s conch shell chart a course to humans connecting their brains to the internet? James Burke's visionary series Connections returns for a new generation. Experience all new Connections. With monthly, annual, and bundled plans, find the one that works for you at curiositystream.com.
Attention car shoppers. Right now at South Carolina Federal Credit Union, you can get a new or used auto loan and pay nothing until 2024. And no payments for 90 days means nothing out of pocket going into the new year. Plus, we have flexible rates and terms, so you could make the best financial choice for you. Learn more at scfederal.org/auto loans. That's scfederal.org/auto loans. Certain restrictions apply. Existing South Carolina Federal credit loans are excluded.
This is SpaceTime, Series 24, Episode 4, full broadcast on the 11th of January 2021. Coming up on SpaceTime, the white dwarf study showing Earth's ultimate fate in all its grisly details, some puzzling new questions about the origin of the universe's heavy elements, and the meteor that must have come from a mysterious unknown dwarf planet. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers studying the atmosphere of a nearby stellar corpse called a white dwarf have been given a glimpse of the ultimate, rather grisly fate of planet Earth. Their observations of the atmosphere of a white dwarf called GD424 have shown telltale signatures of the remains of an Earth-like terrestrial world, destroyed as it was ripped apart and engulfed by the dying star. White dwarfs are the stellar corpses of sun-like stars. Stars shine by fusing hydrogen in their core into helium. When stars run out of hydrogen, hydrostatic equilibrium, that is the balancing act between the outwards push of nuclear energy and the inwards pull of gravity, ceases, and gravity wins, causing the star's core to dramatically contract and compress under its own enormous gravity. As the star contracts, those regions around the stellar core which still contain hydrogen move closer to where the core is and the region where the pressures and temperatures are high enough to allow hydrogen fusion to take place. This triggers hydrogen burning in a shell around the core, and that causes the star's outer layers to dramatically expand. And being further away from the core, the star's photosphere or visible surface gets cooler, and so looks redder. At the same time, the star, now called a red giant, experiences a massive increase in its stellar wind production as more and more material flows out from its gaseous envelope. Meanwhile, much deeper down, the increase in the pressure and temperature caused by the core's contraction eventually gets high enough to trigger a helium flash, fusing the core helium into carbon and oxygen. High-mass stars will then progressively fuse heavier and heavier elements. But smaller stars like our Sun don't contain enough mass to fuse carbon and oxygen into heavier elements, and so the stellar fusion process ends. The star has literally died. The star's outer gaseous envelope eventually drifts away as a spectacular gaseous object called a planetary nebula, in the process leaving exposed the superdense white-hot stellar core as a white dwarf, which will slowly cool down over the eons of time. In trillions of years, the white dwarf will cool enough to become a black dwarf. But that's a long way off in the future. The universe simply hasn't been around long enough for any white dwarfs to have become black dwarfs yet. This is the fate that will ultimately befall our own local star, the Sun, in about 7 billion years from now, and it will also mean the end of the Earth, which will be consumed as the Sun becomes a red giant. The atmospheres of white dwarfs are mainly composed of hydrogen or helium, but between 25 and 50% of all known white dwarfs also show traces of metals in their spectra. Now, astronomers refer to all elements heavier than hydrogen and helium as metals. Scientists have always assumed that these metals originate through the accretion of tidally disrupted planets that were once orbiting the progenitor star. Now, a report in the monthly notices of the Royal Astronomical Society and on the pre-press physics website archive.org has analysed the composition of the atmosphere of one of these white dwarfs, the aforementioned GD424. The authors used ISIS, the Intermediate Dispersion Spectrograph and Imaging System, mounted on the 4.2-metre William Herschel telescope, and HIRES, the high-resolution Enschel spectrometer fitted to the giant 10-metre Keck telescope. They found the white dwarf was about 215 million years old, with an effective surface temperature of 16,560 Kelvin. It had just 100th the mass of the Sun and around 0.0109 solar radii. The authors were able to identify 11 metals in the white dwarf's atmosphere, and that's where it gets even more interesting. The chemicals included oxygen, sodium, manganese, chromium, nickel, silicon, iron, magnesium, titanium, calcium, and aluminum. And that's a composition consistent with terrestrial bodies such as the bulk Earth. As the composition didn't suggest an excess of oxygen, but did show large amounts of trace hydrogen, the authors are speculating that this terrestrial world was also rich in water, another analogue for the Earth, and a glimpse into our own home planet's ultimate fate. This is SpaceTime. Still to come, new questions about the origins of some of the universe's heaviest elements, and new discoveries mean astronomers have more than doubled the number of known high-velocity stars. All that and more still to come on SpaceTime.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
New questions are being raised about how the universe's heavy elements are made. Other than hydrogen, helium, and a little bit of lithium, which were produced in the Big Bang 13.82 billion years ago, all the other elements in the periodic table were made by stars. As we mentioned earlier, elements including carbon and oxygen are produced by nuclear fusion in the cores of stars, and more massive stars produce even heavier elements in their core, all the way up to nickel and iron. But what about those elements on the periodic table which are heavier than iron? They were originally all thought to be produced when massive stars die in powerful explosions called supernovae. But that still can't explain everything. So it was thought the heaviest of all elements, things like gold and uranium, may have been produced through the collision of neutron stars, generating events called kilonovae and short-period gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. Okay, so problem solved. Well, no, it's not. New research reported in the monthly notices of the Royal Astronomical Society and on the pre-press physics website archive.org have raised questions about whether neutron star mergers can really explain the amount of heavy elements observed in the early universe, or whether a new explanation is needed. The issue arose after astronomers developed a new method of studying star formation in galaxies from the dawn of time through to today. The study's lead author, Dr. Sabine Belstead, from the University of Western Australia's node of the International Centre for Radio Astronomy Research, says stars can be thought of as enormous nuclear-powered processing plants. They take lighter elements like hydrogen and helium and, over billions of years, produce the heavier elements on the periodic table, which are found scattered throughout the universe today. Belstead points out that the carbon, calcium and iron in your body, the oxygen in the air you breathe, and even the silicon in your computer all exist because stars created these heavier elements and left them behind when they died. Understanding how galaxies formed stars billions of years ago requires using powerful telescopes to observe galaxies billions of light years away in the distant universe. But nearby galaxies are much easier to observe. Using light from these more localized galaxies, Belstead and colleagues have worked out a way to forensically piece together their star formation history. This allows them to determine how and when they formed stars in their infancy, billions of years ago, without the struggle of trying to observe galaxies in the very distant universe. Traditionally, astronomers studying star formation histories assume that the overall metallicity, the amount of elements heavier than hydrogen and helium in a galaxy, doesn't change over time. But when they used these models to pinpoint when stars in the universe should have formed, the results didn't match up with what they were actually seeing through their telescopes. Belstead says the results not matching up with the observations is a big problem because it tells scientists something's missing. Now, it turns out that missing ingredient is the gradual buildup of heavy elements within galaxies over time. So, using a new algorithm to model the energy and wavelengths of light coming from almost 7,000 nearby galaxies, the authors succeeded in reconstructing when most of the stars in the universe actually formed, in agreement with their telescope observations. And this is the first time that astronomers were able to constrain how the heavy elements in the universe change over time based on their analysis of these 7,000 nearby galaxies. Belstead says most of the stars in the universe were born in extremely massive galaxies early on in cosmic history. But today, most new stars are being formed in much smaller galaxies.
Well, from our perspective, it was trying to understand how can we use observations of nearby galaxies to best constrain that epoch in the universe. So one of the ways in which we've typically understood star formation in the universe is that we look at observations at various redshifts, so various epochs in the universe's past, and we try to make measurements of galaxies and measure the star formation rates, so how quickly galaxies are forming stars at those epochs in the universe. While that's easier for nearby objects, so for more recent things, once you start getting into the first few billion years of the universe, those kinds of observations are really difficult to do. They're being done, and there is a lot of studies undergoing to try and constrain that part of the universe, but we wanted to see whether we could tackle that problem from a completely different perspective.
Why is it difficult to study star formation rates in the early universe long, long ago?
It's difficult simply because the observations themselves are so difficult. So if you're looking at a galaxy that may be existing in the first few billion years of the universe, by the time that light reaches us, that light has been traveling for 10 billion years. The image that we see of the galaxy at that point is very low resolution, very difficult to constrain any features, and you've got various observational biases that we don't necessarily know how fully we understand.
Like reddening and things like that.
Exactly like reddening. We don't actually know how dust behaves in galaxies in the early universe. Currently, we might assume that dust behaves similarly to the galaxies that we see around us. But if there's a different assumption to what the actual truth is, then any measurement we make of the star formation rate at that point won't be accurate.
So the answer is just use nearby galaxies, because galaxies like the Milky Way, hey, they're over 12 billion years old anyway. So can't we get a good idea of what happened early on simply by looking locally?
Exactly right. And it's the kind of thing that in the past we haven't had a huge amount of success at extracting this sort of information. So the reason we think that we might be able to use nearby galaxies to do this kind of work is that, let's take, for example, some of our nearby objects, and for us nearby means anything that has existed in the last 800 million years. So it's still fairly old, but recent in the grand scheme of things. Some of those galaxies will have been formed recently, so their stars might only be a few billion years old, but others might have stars that were formed very early on in the universe. So some of those objects might be very old, so they would have existed 10 billion years ago, but we're seeing them today. And stars that are only a few billion years old look very different to stars that are many billion years old.
I guess the best example of that would be just looking at the halo of our own galaxy, where we have population 2 stars.
Indeed. And so if we look at the night sky, you can see that, especially if we've done it with a camera, we can have longer exposures of the sky. We see that there are redder stars in the sky and bluer stars in the sky, and that essentially applies to galaxies that are bluer and galaxies that are redder, and that essentially comes from the different populations of stars within them. So the idea is that if we can model this multi-wavelength light of galaxies and properly try to backtrack how old the individual stars in the galaxies are, can we identify for a whole population of galaxies when they each formed their stars? Doing this for a good chunk of the universe means that we can then understand for the whole universe what was the changing star formation rate with time, and then try to constrain how the universe was forming stars in the earlier billion years as well, rather than just the most recent epoch.
And that's where ProSpec comes in, I take it.
Yes, it definitely does. So this is referred to as an SED fitting tool. Essentially, a spectral energy distribution of a galaxy is how the brightness of a galaxy varies with wavelengths. So generally we speak from roughly the far ultraviolet through to the far infrared. And then we take images of these galaxies in about 20 different bands. And then we can see, based on this spectral energy distribution, or this SED, can we apply various tools to model that? And Prospect is a new tool that does exactly that.
Looking at 7,000 nearby galaxies, what did you find in terms of, we live in this stelliferous age of the universe. What's Prospect told you about the stelliferous age of the universe?
Well, what Prospect does really well is that it's a tool that is slightly more flexible than its predecessors. And the really important thing that we've done now is say, let's take one of the key assumptions about galaxies, and that's about their metallicity. So in astronomy, we refer to the metallicity of objects, and that's essentially just saying how many elements heavier than hydrogen and helium does a galaxy have. And classically, with the sort of modelling in the past, we've assumed that this metallicity of an object doesn't change with time. The problem is that we know that stars form metals with time. They slowly produce them during the star's lifetime itself, and then when the star dies, it produces an enormous number of metals, and they get released into the environment of the galaxy, and then the new stars that are formed are more metal-rich.
I always had a problem with that original assumption that metallicity of a galaxy doesn't change over time. Of course it does, as stars evolve.
Exactly. And it's important for us to make assumptions with any sort of modelling work. The universe is an incredibly complex environment, and to model everything perfectly is very, very difficult. So it's natural that we make assumptions early on in the process, but it is important that we refine those assumptions with time such that we can improve the kinds of predictions that we make, for sure.
And so as you looked at the evolution of the universe using these models, you found something really interesting in terms of when stars were being made and at what rates.
We did. Well, we found that much like the actual observations at high redshift that have been made, for the first time, this forensic kind of tool has shown us that indeed something like 40% of the stars formed in the whole universe were formed in the first 4 billion years. And so we're really seeing that the highest rate of star formation that we see in the universe was very, very early on. And ever since about 10 billion years ago, we've just seen a slow decline in the amount of star formation that we see throughout the universe up until today.
And it's really interesting, the shape of that curve too, isn't it? It's like there was nothing, then all of a sudden, obviously the dark ages, then all of a sudden there was a sudden burst of star formation, which reached an early climax, and then a very gradual but very constant and very easily identifiable curve back down again.
That's definitely true. Yep. We often refer to this as the early epoch cosmic dawn, and then at that peak of that star formation rate, we refer to that as cosmic noon. And then the epoch we've lived in slowly since then has just been a slow decline since cosmic noon, when the party was really happening, so astronomers like to say.
We're in the afternoon phase now then, aren't we?
We definitely are. And as if we could project ourselves forward billions of years from now, we would see that just simply continue. Well, I don't think there's anything that would stop that slow decline of star formation in the universe at this stage.
So the stelliferous age will definitely come to an end, and the age of the black hole will definitely rise.
Presumably.
Depending on dark energy, of course.
Which we obviously don't understand at all, so who knows what will happen.
What is galaxy downsizing? Tell us about that.
Galaxy downsizing is a term that astronomers like to use to refer to the fact that the objects in the universe that are the largest, so the most massive galaxies in the universe, were actually formed the earliest. That might seem counterintuitive. One might think that the things that are the biggest are those that are still forming lots of stars now and are still growing larger. But it's in fact the opposite that is true. So the most massive things are also those things in the sky that are the reddest, and they're not forming stars right now at all because everything happened early on in the universe. The smallest objects, the smallest galaxies, those things that are the least massive, they're actually the objects that are forming stars now. And simply by modeling the light of these various galaxies, we've been able to recover that trend forensically in this work, which has been really exciting to be able to show that kind of analysis through this style of work.
Is that because things were physically closer together in the early universe?
Partially that's true. Most of it simply comes down to the fact that the amount of stars that were formed was simply so much greater. There was a lot more gas available in the universe, and the star formation rates were really high. But then, yes, because things were closer in the universe, things were very turbulent. You had a lot of mergers between objects. You had smaller things becoming larger through star formation very quickly, and then getting even larger because they were merging with their neighbors. So it's a compounding factor of numerous different things.
Lots of big galaxies close together would mean lots of star formation as well.
Indeed, they egg each other on to form more stars.
It all sort of meshes together nicely, doesn't it?
It definitely does. And the really, really great thing with this kind of analysis with nearby objects that we understand fairly well is that you're starting to understand multiple facets of evolution from a single place. It's learning at it all self-consistently, which is very important to try and bring together the various things we understand about galaxy evolution and move forward for the next step.
And what is the next step for you?
The next step for us is to scale up this study. So this was only 7,000 galaxies that we looked at, which is a lot.
Only 7,000 galaxies.
It's True. Well, I mean, the survey that we were working with was the Galaxy and Mass Assembly Survey, and that has data for about 230,000 objects. And so those are objects that extend all the way out to redshifts of 0.5. So we're looking at probably the last multiple billion years of the universe. And so we've only looked at a small fraction of that, the most nearby things. By expanding that to larger samples, we can start to really look at the large-scale trends with environment. So whether a galaxy is in a galaxy cluster or whether it's all on its own in isolation, how do those sorts of trends also affect galaxy evolution? But even 230,000 objects, while that is large, that's going to be a drop in the ocean compared to the next generation of galaxy surveys that we will have access to in the next few years, that will be looking at millions of galaxies. So the scalability of these sorts of projects is enormous, and I'm very excited to find out where it'll take us.
Do surveys like the Sloan Digital Sky Survey help?
SDSS, so the Sloan Digital Sky Survey, was enormously influential with this sort of work early on. It provided unprecedented amount of information for galaxies. So definitely a lot of this sort of work helps to be developed off the back of surveys like the SDSS. But now we're moving forward into the next generation, even post-SDSS. And so we're looking at larger portions of the sky. We're looking at what we refer to as deeper surveys, which means we're looking at fainter and fainter objects, which allows us to get both things that are further away and things that are smaller that we've missed in the past. And so we're really getting a much more comprehensive understanding of these galaxies in the sky.
That's Dr. Sabine Belstead from the University of Western Australia's node of the International Centre for Radio Astronomy Research. And this is Space Time. I'm Stuart Gary. Still to come, astronomers more than double the number of known high-velocity stars, and the Meteor, which must have come from a mysterious, as-yet unknown dwarf planet. All that and more still to come on Space Time.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
Astronomers have discovered a population of hundreds of high-velocity stars in the galactic halo of the Milky Way. The 591 newfound stars, reported in the Astrophysical Journal, more than double the total number of these objects known. High-velocity stars move through the galaxy at speeds of more than 65 kilometers per second relative to the average motion of stars in the Sun's neighborhood, with some traveling at more than 1,000 kilometers per second relative to the Sun. And that's fast enough to achieve galactic escape velocity, allowing these stars to be literally flung out of the galaxy entirely. They're thought to be accelerated to their high velocities through various types of gravitational interactions, either with other stars or stellar systems, through supernova explosions, through interactions with black holes, or because they already orbit in the galactic halo on highly elliptical trajectories, resulting in relatively high velocities compared to stars in the galactic disk. The newly discovered high-velocity stars were identified using the Large Sky Area Multi-Object Fiber Spectroscopic Telescope, together with the European Space Agency's Gaia Space Telescope. And the authors say 43 of these newly discovered high-velocity stars are moving fast enough to leave the galaxy. The authors determined that most of the 591 high-velocity stars discovered were giants, no longer on the main sequence. And most of the stars were low metallicity, meaning they were ancient. But about 14% were actually high metallicity, and therefore were born in far more recent times. By tracing their orbits back through time, the authors determined that about 15% of the stars originated in the galactic center, 55% are from the galactic disk, that's the same part of the galaxy where our Sun lives, and 30% originated in other galaxies, further proof of galactic cannibalism at work. This is Space-Time. Still to come, the meteor that must have come from a mysterious unknown dwarf planet. And later in the science report, China prevents officials with the World Health Organization from traveling to Wuhan to investigate the cause of COVID-19. All that and much more coming up on Space-Time. Scientists say the parent body of the Almahata Sitta meteorites, which rained down on Sudan's Nubian desert in October 2008, must have come from a yet-to-be-discovered water-rich Ceres-sized dwarf planet. The original 4.1-metre-wide meteor named 2008 TC3 airburst as it hit the Earth's thicker atmosphere at an altitude of about 37 kilometres, breaking into more than 600 fragments between 1 and 10 centimetres wide. The event was unique in that it was the first asteroid impact predicted in advance by astronomers. The new findings, reported in the journal Nature Astronomy, are based on infrared microspectroscopy, electron microprobe analysis, and transmission electron microscopy examination of a 50 milligram sample of the original meteor. Catalogued as Almahata Sitta, or AHS-202, the shard showed that the original meteor was a carbonaceous chondrite, among the most primitive and rarest of all meteors. Carbonaceous chondrites often include water and organic matter in the form of amino acids, the building blocks of proteins. That makes them a potential key ingredient for the development of life. They also contain CAIs, or calcium aluminum-rich inclusions, and that suggests they may have formed directly out of the solar nebula from which our solar system eventually condensed some 4.6 billion years ago. In other words, they can be as old, if not older, than the solar system itself. And the aluminum in the inclusions, well, that's thought to come from the supernova, which triggered the birth of our solar system in the first place. While many carbonaceous chondrite meteorites are dominated by minerals formed either through exposure to water at low temperatures and pressures or heating in the absence of water, very few show evidence of metamorphism in the presence of water under intermediate conditions. Until now. Scientists with the Southwest Research Institute found a range of hydrated minerals including amphibole. Amphiboles are rare in carbonaceous chondrite meteorites, having only been identified as a trace component in the Allende meteorite. That suggests intermediate temperatures and pressures, and a prolonged period of aqueous alteration on the parent asteroid. And in order to reach those sort of pressures and temperatures, the parent asteroid would have needed to be somewhere between 640 and 1,800 kilometres in diameter. The simple fact is, most carbonaceous chondrite parent bodies are thought to be less than 100 kilometres in diameter, and that means they simply wouldn't have enough mass to produce the range of pressure and temperature conditions represented by the minerals found in AHS-202. So, the findings suggest that 2008 TC3 must have been part of a much larger body, something about the size of the dwarf planet Ceres, the largest known object in the solar system's main asteroid belt between Mars and Jupiter. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. China has refused to allow World Health Organization officials to travel to Wuhan to investigate the origins of the coronavirus pandemic. The deadly virus is now suspected of escaping from the Chinese government-run Wuhan Virology Lab a year ago. It's killed almost 2 million people and infected some 90 million others. Australia led calls for an independent inquiry into the origins of the Wuhan virus, which was eventually backed by a global coalition of 137 countries at a meeting of the World Health Assembly in May. But China weren't pleased, with Beijing triggering a raft of retaliatory trade sanctions against Australia. Canberra's call for an investigation followed concerns over Beijing's early cover-up of the virus and the role the World Health Organization played in that cover-up. Meanwhile, in other COVID-19 news, the European Union has just approved the Moderna COVID-19 vaccine, which is only the second cleared for use in the EU following the Pfizer-BioNTech jab. And the Australian government has announced that it will accelerate the start of vaccinations from March to mid-February in the wake of a new, more contagious UK strain of the virus. By the way, has anyone noticed how the people who complained about COVID-19 being called the Chinese flu or Wuhan flu haven't complained about use of terms like the UK strain or South African strain? Australia's Bureau of Meteorology says 2020 was Australia's fourth warmest year on record, despite it being a La Niña year which typically reduces temperatures. It found Australia's climate has warmed by an average of 1.44 degrees Celsius since national records began in 1910, leading to an increased frequency of extreme heat events. The Bureau also found there's been a decline of around 16% in April to October rainfall in the southwest of Australia since 1970, with the May to July rainfall total showing the largest decrease, around 20% since 1970. Meanwhile, the southeast of the country has seen a decline of around 12% in April to October rainfall since the late 1990s. Overall, there's been an increase in extreme fire weather, a drop in the number of tropical cyclones, an increase in ocean temperatures by 1 degree Celsius, and a rise in average sea levels. Globally, concentrations of atmospheric greenhouse gases are continuing to increase and are now at their highest level in 2 million years. Iran has told the International Atomic Energy Agency that it's going to start enriching uranium up to 20% purity, well beyond the 3.67% threshold it agreed to under the United Nations 2015 Nuclear Non-Proliferation Treaty. The news follows a report by the United Nations nuclear watchdog in November 2020 that Iran's nuclear stockpile of enriched uranium was now more than 2,442.9 kilograms, up from 2,105.4 kilograms of enriched uranium reported on August the 25th. Now, to put that in perspective, that's more than 11 times the 2002.8 kilogram limit Tehran agreed to under the Vienna Accord, and more than double the amount needed to make a thermonuclear weapon. Even more sinister, Tehran has prevented United Nations independent atomic monitors from carrying out inspections at several nuclear sites, again a violation under the 2231 resolution. It follows a report by the International Atomic Energy Agency in June last year, which criticised Iran for scrubbing possible former nuclear facilities. And it warned that the Islamic Republic was continuing to hide possible undeclared nuclear material and nuclear-related activities. The UN agencies also raised serious concerns about a missing metal disk of uranium, the type used in a thermonuclear weapon, and the location of other undeclared nuclear material that's been missing since Iran's early nuclear research activities in the early 2000s. Meanwhile, Tehran has also continued its development of long-range ballistic missile technology capable of delivering thermonuclear warheads, another violation of the 2015 treaty. The oil-rich nation insists its nuclear program is exclusively for peaceful power generation. Handing leftovers to wolves during harsh winters may have led to the early domestication of dogs around the end of the last ice age between 29,000 and 14,000 years ago. The findings, published in the journal Scientific Reports, suggest that while humans would usually have killed off any species that might hunt the same foods as people do, humans instead had an excess of meat which they shared with the wolves. The authors say feeding wolves in this way, in combination with using them as hunting aids and guards, is probably the reason you can put silly Christmas sweaters on your pet pooch today. Researchers have just completed one of the most comprehensive surveys ever undertaken on people's attitude towards vaccines. But unlike most surveys which directly ask participants questions, this one identified dominant vaccine narratives on social media platforms in English, French and Spanish online communities. Researchers found that those who don't trust vaccines seem to fall into one of two generally equally divided groups. There are those who are concerned that the vaccine itself might be unsafe. That follows scare campaigns like the false claim that the combination measles, mumps, rubella vaccine caused autism. And then there are those who simply don't trust the government's intentions, and that's based on unethical government-sanctioned experiments such as Imperial Japan and Nazi Germany carrying out brutal experiments on prisoners and civilians through groups like Japan's Unit 231 or individuals like the Nazis' Josef Mengele. And of course, the United States isn't immune from these sort of brutal experiments. There was the Tuskegee syphilis study, which deliberately infected black men to see how syphilis could run its course, and the CIA's Project MKUltra, using mind-altering drugs on people to see if they could brainwash them and turn them into Manchurian candidates. Tim Mendham from Australian Skeptics says the researchers from First Draft looked at some 14 million posts to gauge people's opinions.
A survey was done, a pretty huge survey, looking at claims of that COVID was a conspiracy or whatever. They looked at something like 14 million posts. It was in a whole range of languages over a period of about 3 months, and they whittled that down to, obviously a lot of posts were just sharing and that sort of thing and not really adding anything of value to the discussion. They whittled it down to about 1,200, I think, in each of those 4 languages they're looking at. And each of and they themselves elicited 13 million responses. What it comes down to is that the anti-vaccination movement, judged by these social media posts, is pretty evenly divided between fear of the vaccination and fear of government control or government over-influence. That there are those who obviously claim conspiracy. As far as governments, they're all just trying to sort of control us. They're putting things in the vaccinations.
Yes, little nanobots in the vaccinations so they can keep an eye on you. This is all being done by big tech companies in collusion with governments. Yes.
That's right, yeah.
I've seen
and trying to control our lives, etc. And then there are those who have unfounded fears that vaccination causes autism, blah, blah, blah. So, whereas some time ago it might have been the case that people feared the vaccination having side effects that was perhaps announced, and that therefore the vaccination was wrong. Now it's the people supporting vaccination, which is being seen by conspiracy theorists, which is the issue. At least 50-50 is the split. So this sort of move towards fear, suspicion of governments, which in some cases is well-founded but not always,
Indeed.
Is actually a growing one, and it actually is applying more broadly, obviously, outside of the vaccination area. You just need to look at the 5G arguments at the moment and then combine the 5G arguments and the anti-vaccination argument and all sorts of areas, as we've spoken many times about conspiracy theories, etc. Once upon a time, governments made mistakes, which they have. Now it's governments doing conscious evil acts, according to these people posting on social media. Social media is a great place to spread your theory. To point out, you need a theory first, and social media is the tool, but certainly you can spread your media a lot wider and a lot faster than you could have in years gone by.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.